Hi everybody, I want to take you through some notes about multiplication rules for probability. I'm going to look at things like independent events, dependent events, and some conditional probabilities. The notes are a little bit long, as you can see here, so feel free to stop the video as needed, maybe per day or per little bit of information that you need. But I'll just go straight through and then you deal with the video as you need. Okay, so here we go. We say that A and B are independent. A and B are independent if the fact that A occurs does not affect the probability that B occurs. Okay, for example, rolling a die and getting a 6, then rolling again and getting a 2. The fact that we get a 6 and then roll again and get a 2, the 6 doesn't affect the fact that you get a 2 on the second roll. Or the second example here, drawing a card and getting a king, putting it back, and drawing a 10. The fact that you draw a king and then you put it back and draw a 10, one thing doesn't affect the other, so therefore the events are independent. Okay, so rule 1 for multiplication. When two events are independent, the probability of them both occurring is given as the probability of A and B. You take the probability of A times the probability of B. Okay, please note the word and. Okay, so and means multiply. Okay, let's look at a couple examples. A coin is flipped and a die is rolled. Find the probability of a head and a 4 occurring. All right, so again, probability of head and 4. We're going to do probability of head times the probability of a 4. All right, so when you toss a coin and get heads, the chance is 1 out of 2. Times when you roll a die and get a 4, the chance is 1 out of 6. So you multiply top times top is 1. Bottom times bottom is 12. So we'd say our probability here is 1/12. Okay? All right, next one. When a single die is rolled, and I should have put here the word twice. So we're going to roll it 2 times. The probability of an even number and a 4. Okay, so probability of even, well, there's 3 evens on a die, so 3 out of 6 times chance of a 4, 1 out of 6. So when you multiply top times top, you get 3. 6 times 6 is 36. And if you reduce, you'll get 1/12. Okay, coincidence that it's the same as A, or the first example, but it is what it is. All right, next one. A card is drawn, then replaced, then a second card is drawn. Okay, since it's replaced, we can claim the events are independent. All right, chance of a queen. Well, there are 4 queens out of 52 cards in a deck. Aces, there are 4 aces out of 52 cards in a deck. Okay, you could reduce these first before you multiply if you like. If you don't, it comes out like 16 over 2704. And then that'll reduce also for you from there, 1 out of 169. If you do this division, 16 divided by 2704, and then do math on your calculator and then frac, that will reduce it for you. So if you get into something too big, you could always try the math frac and see if that'll help you. Okay? All right, example 4. The probability that a medical test will show positive is 0.32. Okay. If 4 people are tested, find the probability that all 4 will show positive. All right, so my thinking on this one is, as I read it, I need a positive and a positive and a positive and a positive. Okay, so if I've got 0.32 is my chance of positive, I'm going to just do that 4 times multiplied. Okay, some people like to use an exponent. And that would be absolutely fine. And your answer comes out to be 0.01, and you're good to go, okay? Actually, I would use the exponent because you got 0.4 or 32 to the fourth, and you got it. All right, so that was all about independent events, okay? Next, we're going to scroll down and take a look at dependent events. Dependent events. The outcome of the first event affects the outcome of the second event in such a way that the probability is changed. Okay, so this time the first event affects the outcome of the second. Okay, so what do we have here? Draw a card, not replacing it, drawing again. That's dependent. Draw a ball from an urn, not replace it, draw another ball. Both are dependent events. Okay? So we'll run on down here. So this is where we bring in the word conditional. Okay? The conditional probability of an event B in relationship to event A is the probability that B occurs after A already occurred. Okay? So our dependent probability rule looks like this. Probability of A times the probability of B given that A already happened. All right, so this little line here says given that. Given that, okay? So this is the probability of B given that A already occurred. Okay, so example. In a shipment of 25 microwaves, 2 are defective. If 2 ovens are selected at random, selected and tested, find the probability that both are defective if the first one is not replaced after it has been tested. All right, so the chance the first microwave is defective is going to be 2 out of 25, okay? We take that microwave, we throw it out in the dumpster, then we take a look again. Well, since we got rid of the first one, now there's only 24 microwaves. Since we got rid of one of the bad ones, only 1 remains. So now we have that this is 2 out of 600. And if you reduce, you get 1 over 300. That's your probability. If you'd like a decimal, it's around 0.003. Okay? All right, next one. WW Insurance Company found that 53% of the residents of a city had homeowners insurance with the company. Of these clients, 27% also had auto insurance with the company. If a resident is selected at random, find the probability that the resident has both the homeowners and auto insurance with the company. All right, so probability of homeowners and auto. Okay, well, homeowners, let me see here. Homeowners, 27%, nope, I lied. 27, okay, is auto, my bad. 53% is homeowners. You'd think I'd have the answer since I wrote the question, right? Okay, so we'll do 0.53 times 0.27, and we get 0.143, and there's your probability of both. All right. Okay, very nice. Okay, so if you're using your notes, we'll flip over to the second page and continue with a couple extra examples here. Okay, so next up is some examples with cards. If you need to know playing cards, there's a reference sheet in your Schoology if that would be helpful for you. Okay, so here we go. 3 cards are drawn from an ordinary deck and not replaced. Okay, find the probability of getting 3 jacks. Okay, so in a deck there are 4 jacks. We know there's 52 cards in the deck. So the first jack, 4 out of 52. You pick one, you throw it out, Now there's 3 jacks left out of 51 cards. Throw it out. 2 jacks left out of 50 cards. Okay? Multiplying all together, you get 24 over 132,600. And that actually reduces to 1 over 5,525. Okay, and you're done. All right, next one. Probability of an ace and a king and a queen. And again, no replacement. Okay, so we start out, there are 4 aces out of 52 cards. Okay, take one, throw it out. There's 4 kings, but now there's only 51 cards because we took away an ace. So we throw out a king. Queens, there are 4 queens, and now there's only 50 cards left. All right, so in multiplying this together, you get 64 out of 132,600. And this one happens to reduce to 8 over 16,575. Okay, moving along here. Club, spade, heart. Okay, so the different suits, there are 13. So there's 13 clubs out of 52. Take one, throw it away. 13 spades, but now there's only 51 cards left. Take one, throw it away. Hearts, there are 13 hearts, and now there's 50 cards remaining, because again, each time we are not replacing the previous. So this one multiplies to be 2,197 over 132,600, reduces to 169 over 10,200. Okay? And lastly, for cards, we have 3 clubs, okay? My 3 clubs. So we have 13 clubs out of 52 cards. Take one, throw it away. The chance of another club is now 12 out of 51. Take one, throw it away. And lastly, 11 out of 50. This lovely multiplies into 1,716 over 132,600. And it reduces to 11 out of 850. Okay? All right, nice example there with some playing cards. And now we'll move on to a conditional probability formula. Okay, probability of B given that A already happened. All right, it's the probability of A and B on top divided by the probability of A. Okay, so to me, you want to kind of follow the pattern here. So we want the probability of B. A already happened is what this is. So this is B given that A already happened. All right, let's take a look. So a box contains black and white chips. A person selects 2 chips without replacement. That's important. If the probability of selecting a black and white chip is 15 out of 36, and the probability of selecting a black chip on the first draw is 7 out of 8, find the probability of selecting a white chip on the second draw, given that the first chip selected was a black chip. All right, so we want the probability of a white chip given that a black one was picked first. All right, so we need on top the probability of black and white divided by the probability of black. And again, follow the pattern. The black was second, so that's where it shows up. When you go through and calculate. All right, so the black and white number is this one right here. Black and white, 15 out of 36. All over the probability of a black chip, 7 out of 8. Okay, so then you got to remember how to do fraction math. So you've got 15 out of 36 is divided by 7 over 8. So take 15 over 36 times the reciprocal. 8 over 7. And if you do a little simplifying ahead of time, you can break this down, 30 over 63, and that breaks on down to 10 over 21, or 0.48 for the probability. Okay, and all I did here, I simplified this a little bit. I made that 2 and this 9, and that's where I got 30 out of 63, even though that looks funny. Okay, couple more examples here. And again, I hope that as you're watching this, you pause and so forth when you need to, for the sections that you're interested in. All right, so this is conditional example 2. A survey asked 100 people if they thought women in the armed forces should be permitted combat. The results of the survey are shown. Okay, the only thing I noticed here from my notes, I think it'd be good if we added a total to this part of the chart. So we have here a 40, a 60, and then the grand total here in the corner of 100. Okay, I think we might need that, so we'll add that in there. So it says, find the probability a respondent said yes and was female. Okay, so my interpretation of that is yes, given that the person's female. Okay, so in following the pattern, we want to do probability of female and yes divided by the probability the person's female. Okay, so again, I'm kind of following the pattern. What I already know, female, appears here and on the bottom. All right, so let's see what we get here. So female and yes. So female and yes. Female yes is there. The number looks to me to be an 8 out of the grand total of 100. So we're going to do 8 over 100. And then probability of female. So go across here to the total. Female, 50. And the grand total there is still 100. So we're going to have 50 over 100. And then when you have a fraction out of fractions, well, I'll show you it this way first. If you do 8 over 100 divided by 50 over 100, that becomes 8 over 100 times the reciprocal, 100 over 50. So what happens is those 100s cancel. You have 8 over 50, which reduces to 4 out of 25. Okay, now, fun fact, if you notice the complex fraction, these denominators are same at the beginning, you can go ahead and reduce from there, and that takes you directly to the 8 over 50, which is what I had here, and you can reduce it to your final answer. Okay, so you just kind of want to watch for that. Okay, so let's run through a second one of these from the same chart. Find the probability a respondent was male given that the respondent answered no. All right, so we have male given that they answered no. So we'll go probability of, okay, and remember the pattern, no and male divided by the probability of no. Okay, so again, follow the ends here, here, and here. Okay, there's a pattern to it. Okay, so here we go. No and male. No and male. I see that to be 18 out of 100. All over probability of no. Okay, probability of no. Sitting right there at 60. So we got 60 over 100. And if we reduce here, we've got 18 over 60. And that'll reduce down to 3/10. Final answer. And if you have decimals here on these, it's okay. All right. All right, so that's a little section on conditionals. Okay, there's more to come on those, more detailed on another video. Okay, but at least gives you a little idea. All right, then we're going to wrap it up here. Probabilities for at least. That's our next section. Okay, so we have probabilities for at least. This one goes, a coin is tossed 5 times. Find the probability of getting at least one tail, okay? So whenever it's probability of at least, okay, we want to go in a little pattern like this. If it's at least, you're going to do 1 minus the probability of, I'll say like the opposite. So if I'm asking for one tail, I want to do the 1 minus the probability of all being heads. So you feel like it's the opposite. Okay, so in this case, this will be 1 minus the chance of heads is a half, and we wanted to toss it 5 times, so it's going to be 1/2 to the 5th power, which is 1 minus 1 over 32. And if you do that, you get 31 out of 32. Final answer. Okay. And then what else do we have here? A game is played by drawing 4 cards from an ordinary deck and replacing each card after it is drawn. Find the probability that at least one ace is drawn. All right, so we want to do probability at least one ace. So that means we want to do 1 minus the probability of, I'll write it like this, no aces. Okay? All right, so there's 4 aces in a deck out of 52 cards. So that means 48 of them are not aces. And we're going to do 4 draws. So we should take this to the 4th power. Okay, and honestly, I guess I lost my notes on this, so I got to grab my calculator quick. Sorry about that. So let's see here. If we take 48 out of 52, so you could think of this as 1 minus 12/13 to the 4th if you want. So if I do that, 1 minus, okay, I'm getting this to be about 0.27, and that's the best I've got. I just took it to a decimal, okay? All right, well, hopefully that's good. There is a dedicated video to both of these last sections, both the conditionals here and the probabilities for at least, with some more detailed examples, okay? Well, I hope something in here is helpful to you. Again, this was just intro notes on multiplication rules for probability, independent versus dependent events. Have a superb day, and thank you for watching.